Hello friends, in this video we're going to discuss about velocity of transverse wave along a stress string. So now let us consider a string. This is the string, suppose, and it is stressed by a tension T. Okay, so tension on this string is T, right? And this string is lying on x-axis, suppose. Let me consider this way. This is lying on x-axis. Okay, this is lying on x-axis and PQ is the string here. Okay, PQ is the string. So now you see here, this O is the center of the string. Now it is pulled in the upward direction. Okay, so that it takes this shape. Let me show you. So it is plugged at the center in upward direction, so that we get this shape, right? Now let us consider a very small length element of this stressed string. So that is, suppose AB. Let me take this as A, this point is B, right? And width of this is, suppose, dx, very small, it is dx, right? Now you see tension at this point A, due to this part, will be in this direction. If you draw a tangent here, if you draw a tangent here, okay, so in this direction the tension T will be, tension on the string at this point A will be in this direction. Okay, and similarly at B, the tension will be in this direction. That again will be along the tangent at B, right? Similarly, as you can see that tension at A will be along tangent at the point A, and similarly the tension at B will be along the tangent at drawn at B, right? That's drawn at B. Okay, so here is the direction of the tension here, and so this is tension at B and this is tension at A. Okay, and these two tangents makes angle theta n. This angle is, suppose, theta. Let me consider this is theta, and angle between and this angle is smaller than this one by very small angle, that is theta minus del theta. Okay, theta minus del theta, let me consider that way. Okay, and hope you have understood this. So now you may be confused about this T here and here to opposite direction. You can assume this way that suppose this is the element AB, okay, and this end is tied with another string, and at this end there is a mass or load, something. Okay, here you see. So tension in this string at this point will be in this direction. Tension at this point on AB will be in this direction, right, in opposite. So that's how we have considered that these two, tension at B and tension at A, will be in these two directions. Okay, so hope you have understood this. So let me show you, let me draw it clearly. So just give me a second. This is the tension at B, tangent at B, so direction of the tension will be this. Okay, hope you can understand clearly. Hope you can see this. Okay, and you see this. Let me do one thing. Let me consider this is, instead of del x, let me consider delta x. So sorry, instead of dx we have considered here it is delta x. This part is delta x. Okay, this part is delta x. Now you see here. Okay, let me write all the things that I have considered here. Okay, so pause the video, write what I have considered. I have written here. So here you see, so this string is plugged, that means it is pulled upward in upward direction at the center, and here I have considered a very small element AB, and its length is delta x. Okay, delta x. I have considered this length is delta x, so which is approximately equal to this. Now you see, as this AB segment is very small, so it must be equal to this part. Okay, here you see this. Okay, so that means these two equal, these two are equal. Okay, now you see these tensions at A and B can be resolved into rectangular components, right? So now you see, so here suppose this point is A, this point is A, and here is the tangent, and this is the direction of the tension, which makes angle theta with the x-axis, right? So it must have two components, one is this, another is this. Okay, so if this angle is theta, then this must be also theta, alternate interior angles. Then this component, this horizontal component must be t cos theta, and the vertical component must be t sin theta, right? T sin theta. Okay, so now, so the component of the tension due to which this string tends to move towards the equilibrium position, to the original position, that is the downward component, which is t sin theta. Okay, tension, the downward component of tension at A, the downward, sorry, let me write here, the downward component of tension T at A is, there is nothing but, you know, t sin theta, t sin theta, right? T sin theta. Now for very small theta, we can write sin theta is approximately equal to theta, and tan theta is also approximately equal to theta. So that's why we can write that sin theta is equal to tan theta. That's why you can write sin theta is equal to tan theta. Hope you have understood this. So now you see here, and you know that we know that tan theta gives if this angle is theta, tan theta gives the slope of this tangent, right? Slope of this tangent, and slope of the tangent will be represented by dy by dx, differential coefficient. Hope you know the, if you know the definition of derivative, right, differential coefficient, then you must know these things. Okay, so we can write tan theta, which is nothing but dy by dx, which is nothing but slope of the tangent at A, right? Slope of the tangent at A. So that's why what we can say that this sine theta can be replaced by tan theta, and hence tan theta can be replaced by dy by dx, right, from this equation. So therefore, combining these two results, sine theta is the downward component, right? So as we can say that for very small theta, sine theta is equal to tan theta approximately, which is equal to dy by dx. So we can write that downward component is tension T dy by dx. We can write this way. Okay, this is the downward component of tension. So let me write that on the on another slide, new slide. Let me copy the diagram first. We're gonna need the diagram again, so I don't want to come back to this slide. So okay, so here is the figure, and so finally what we have got, the downward component of tension at A is, as we have got that tension is T sine theta, and also I have told you that sine theta is approximately tan theta for small theta, and tan theta we have got dy by dx, right? So that's why downward component is tan dy by dx, right? Now rate of change of the slope with respect to the length of the element. Now here you see the slope at this position and slope at this position will be different at A and B, as we are getting two tangents, this one and this one. So that's why the dy by dx will vary with the length of this, along this length of the element, right? So now you see what we can do, the rate of change of slope, rate of change of the slope, and with respect to the length, with respect to, let me write here properly, with respect to the length of the element. Now you see slope is given by dy by dx, and rate of change of slope, we know rate of change is given by differentiation, the differential coefficient, and with respect to the length, so here we are taking x. Okay, this is along the length of this element, right? So which will be equal to second order derivative of y with respect to x, right? So that means the change in y with respect to x. Okay, and this dy by dx is nothing but change in y with respect to x. Okay, rate of change in y with respect to x actually, and the rate of change of this rate of change with respect to x is this, right? That means the rate of change of the slope will be different at A and B. So what will be the slope at B? Now you see, therefore now you see, as this gives the rate of change of the slope, then what will be the difference between the slope at A and B, slope of the tangents at A and B, and the length between A and B, the length AB is delta theta, so we have to multiply delta theta with this rate of change of slope. So therefore we're gonna get the change in slope at B is second order derivative of y with respect to x. That means this rate of change of slope into delta x. We need to multiply delta x, the length of the element AB, right? So therefore now you see the tangent, this is the tangent at A suppose, and tangent at B is this. Okay, and you see the angle made by the tangent and tangent at A with x-axis is greater than, that is obviously greater than the angle made by the tangent at B with respect to with the x-axis is smaller, because you can see it clearly from the diagram. Let me make it larger so that you can understand clearly. Sorry, let me show you something. Just give me a second. Okay, now you see this is A and this is suppose B. Okay, so here which angle is greater? Obviously this one, right? Obviously this one is smaller, right? Hope you have understood this. So that's why the slope of this tangent, which makes a smaller angle with the x-axis, its slope will be less. By how much? By this. Okay, so therefore slope at B that will be equal to slope at A minus this. Okay, we know that slope of the tangent at A is given by dy by dx, and at B it will be reduced by this much, because this is the change in the slope, right, at B. So hope you have understood this. Now the tension at B, okay, the tension at B can be resolved into two components. One is this, another is this, vertical and horizontal, right? So here you see, let me draw the diagram again here. This is at A, this is at B. Tension at A is in this direction, tension at B is in this direction, right? Okay, and this tension can be resolved into two components this way. So just give me a second. You see, let me draw the tangent at B only. This is the tangent at B, suppose. Okay, and tangent at B, sorry, tangent at B, it makes angle theta minus delta theta with x-axis, and this is the tangent T. So this horizontal component is T. This angle will be also corresponding angle delta theta minus delta theta. So T is equal to cos of theta minus delta theta, and the vertical component will be T sine theta minus delta theta, right? That's what we get. Now for very small angle, this vertical component will be for very small angle. So sine theta minus delta theta will be tan theta minus delta theta. So the tension upward will be T tension tan sine theta delta theta will be equal to tan theta of tan of theta minus delta theta, right? Hope you have understood this. So for very small angle, first let me write the upward component of tension at B is T sine theta minus delta theta, and for very small angle, theta is very small, theta minus delta will be very small as well, right? So for this small angle, sine theta minus delta theta is approximately equal to tan theta minus delta theta, right? So that's why this upward component can be written as T tan theta minus delta theta, right? So therefore Therefore we can write the upward component of tension at B is let me go to the new slide. Okay, so we can write tension at B is 10 theta minus delta theta. That's what we can do, right? Now let me copy the diagram. Okay, sorry. Okay, and also let me copy this step, that the upward component of this downward component of tension at A, this one. Okay, let me write that one here. You don't need to repeat it, okay? So but we're gonna need this information, that's why I have written here in this new slide. Okay, don't repeat it once you have already written. Okay, so now you see we have got upward and downward component. So here we have got upward at A we have got downward tension, and at B we have got upward tension. So net tension at this segment, okay, resulting downward tension will be, because you see when this is pulled upward, then this string will try to go downward. So that's why there will be a resultant tension, downward tension. Okay, therefore the resultant downward tension, resultant downward tension, resultant downward tension will be equal to upward tension, which is nothing but this one. And as we are writing here the tan theta, so let me write one more thing. This tan theta, okay, just give me 1 second. Let me have enough space. Okay, let me write this one here. Now you see this tan theta minus delta theta is nothing but the slope at B, that is the slope at B. So what was the slope at B? Let me show you. This was the slope at B. Here you can see this is the slope at B. Let me copy this, the result. Okay, sorry. So let me copy this result. Okay, so here is the slope at B. So we can replace the tan theta by this value. Okay, so that's why this is equal to tension T into this dy by dx minus second order derivative of y with respect to x into delta x. Okay, so hope you have understood this. So now the resultant tension, downward tension, will be downward tension, that is T dy dx minus upward tension, that is T of dy by dx minus second order derivative of y with respect to x into delta x. So this is the resultant tension. Hope you have understood this. Okay, so let me write it properly. Okay, sorry. Okay, this is what we have got. Okay, so let me represent this by F force. Okay, now you see, let us consider that let M is equal to mass per unit length, mass per unit length of the string, mass per unit length of the string. Therefore mass of the element, mass of the element of length delta x of length delta x, which is AB, nothing but AB, right? Sorry, delta x is that mass will be, let me erase this part, okay? Sorry, just okay. Now that mass will be, if this is mass per unit length m into the length of the element delta x, right? That is the mass of this element AB, this AB element, right? Hope you have understood this. Okay, now let me simplify this part. Let me copy this and let me go to a new slide. Okay, just give me a second. So we can do one more thing. Okay, sorry. So here, just okay. So now open this bracket and simplify this. Then what will happen? T dy by dx will be cancelled by this, right? Because we have minus between them. Then we end up getting t into second order derivative of y with respect to x delta x. That's what we will get. Because you see, if you remove this bracket, if you open this bracket, then this minus and this sign will be minus, sign will be plus, and these two will be cancelled, right? Hope you have understood this. So that is what we have done. Okay, now here you see, this is suppose equation number 1. Let it be equation number 1. Now you see, let me do it remaining part here. Let me do the remaining part here. So acceleration of the element in the direction of y, this acceleration of AB in along y axis, okay, along y axis will be given by, we know that if displacement takes place along y axis, then velocity is given by dy by dx, sorry, dy by dt with respect to time t. We have to differentiate displacement with respect to time t, and if you need to find the acceleration, then again you need to differentiate the velocity with respect to time t. Then you get second order derivative of y with respect to t, right? That's it. So that's why acceleration of the element AB along y axis, therefore acceleration of AB along y axis, that will be given by second order derivative of y with respect to time t. If this is the acceleration, and we also have got the mass equal to this, and we know that mass into acceleration is force, therefore F is equal to the net force acting on that element m will be given by m delta x into acceleration second order derivative of y with respect to time t. So this is equation number 2, and from 1 and 2, from these two equations 1 and 2, so what we get, this must be equal to this one. Okay, let me copy these two equations and let me go to a new slide. Okay, let me copy the equation number 1 first. Okay, so here is the equation number 1. Let me paste here. Then what was the equation number 2, and let me copy and paste the equation number 2. This was equation number 2. So from 1 and 2, from equation number 1 and equation number 2, what we get the, let me take the right hand side of the equation number 1, sorry, okay, this one, right? And equation number 2, right hand side of equation number 2, that is m delta x second order derivative of y with respect to time t. That's what we get. Hope you have understood this. Now you see what we need to do here. This delta x and delta x cancels, right? These two cancel each other, so delta x gone. So we end up getting second order derivative of y with respect to t is equal to tension T by m second order derivative of y with respect to x, right? Hope you have understood this. M is brought to this side, right? So to get t by m. So hope you have understood this. Now comparing this equation, with the differential equation of plane progressive simple harmonic wave, that is second order derivative of y with respect to time t is equal to v square, which is velocity of the wave. V square is equal to v square into second order derivative of y with respect to x, right? So comparing with this equation, what we get t by m is equal to nothing but v square, right? Comparing with this, we get v square is equal to t by m. If v square is equal to t by m, therefore v must be equal to root over t by m. So this is the velocity of propagation of wave in a stress string, right? So here is the velocity of transverse wave along a stressed string, right? So this is what we needed to find. Okay, so hope you have understood this. Thank you for watching. See you in the next video. Bye bye.